In this example, we have a vapor power cycle with reheat. So this is a Rankine cycle with reheat. The working fluid is water, and we have two turbines. You can see them. Just give me a moment here. So we have one turbine here and another turbine here. So this is the first stage turbine, and then I'm sorry. This is the first stage turbine, then this is the second stage turbine. And we're told that the conditions of the water, which is the working fluid, at all of the various states here. So the table here gives the various states and the quality, specific enthalpy, pressure. We're also told the mass flow rate through the system is 2.1 kilograms per second. And the pump and turbines operate adiabatically. Determine the net power developed by the cycle, so the net power. So to find the net power, we want to include the power generated by each of the turbines and then subtract out the power of the pump. Then we want to find the thermal efficiency of the power cycle. So this will be our typical formula for thermal efficiency for a power cycle. It'll be the net work out of the cycle divided by the heat put into it. And so the heat put into it will be coming in to the boiler, so we need to include that. And then sketch the cycle on a TS plot, including states, paths, and isobars. All right, so let's get started. First of all, just from conservation of mass, the mass flow rate everywhere will be 2.1 kilograms per second. So you can see that it all just follows this path. So it's all just one path, so it'll all have the same mass flow rate. So we'll just call that mass flow rate m dot. Now to find the net power developed by the cycle, what I'm going to do is just draw a control volume that surrounds the pump. And I'm just going to draw it like the following. So it'll be that's the control volume I'll use for this particular example. You could also do individual control volumes around each turbine and the pump, and then add the power for all of those, combine the powers. So either way you want to do it is just fine, but I'm just using that particular control volume. I'm going to apply the first law to that one. I'll write out the whole first law just this time around. This by now should just be very straightforward for you. You've done these first law analyses many, many times. So you're very familiar with this. We'll say that this is a steady state system, so that left-hand side goes to 0. We're going to neglect kinetic and potential energy effects. We've talked about that many times before. We're saying that the turbines and the pump are adiabatic, so there's no heat transfer. So that's equal to 0. And then we'll rearrange this to find the net power out will be the mass flow rate. Now we need to include all of the inputs, right? So we'll include everywhere it comes in. So we have it coming in here. So let me highlight all the ones where it's coming in this kind of orange color. So we have coming in at state 5. It's coming in at state 1 right there. Coming in at state 3 right there. Okay, so let's mark all those. So this will be H5 plus H1 plus H3. Okay, so we have all those, and then we need to, so these are all the ins, and then we have the outs. It's the same mass flow rate going out. So the outlets will mark in a kind of bluish highlighter. So it's going out at state 6. It's going out at state 2. It's going out at state 4. So we'll include those. So again, just to mark this is the in, and these are the outs, right? Well, we are given the mass flow rate. Right, the mass flow rate in the problem statement was 2.1 kilograms per second, and we know all of the specific enthalpies at all of the various locations. So I should call this out net, by the way. And the reason I say net, because there's actually power coming in through the pump here, and then we have power coming out from the two turbines there. So this value of power that I'm including for that control volume is the net power out. So when you plug in those numbers, we'll get the net power out is 2150 kilowatts. Okay, so I don't think there's anything particularly tricky about this example. You've done this sort of thing before many times. The only thing that's different between this example and the previous ones is we now have a two-stage turbine, right? And we have this reheat coming in. So you just have a little bit additional bookkeeping to keep track of. All right, the second part of this example is to find the thermal efficiency of the power cycle. Now, the thermal efficiency for the power cycle is going to be the net power out, which we just calculated, divided by the Q dot in. Right? So we need to find where we're adding heat into this system. Okay? So when you come back up here, the control volume that we'll use for that part of the problem, the heat is coming in through the boiler, so we want to draw a control volume around the boiler. Let me do this in a different color. Let's use a kind of a bluish color. So here's the boiler. We're going to draw the control volume around that and apply the first law there. So first law to the boiler. And I'll just refer back to this first law expression up here. We know that it's steady state, neglecting kinetic and potential energies. And of course it's a passive device. It's not adiabatic because we're actually adding heat. So let me simplify that. So we'll have 0 is equal to m dot. So the flow coming in, let me erase the other kind of highlights. There we go. So let me get rid of the others. Okay, so where we have flow coming in to our boiler, we have it at state 6. It's coming in. It's also coming in at state 2, right? So we need to include both of those. So this is the mass flow rate in term. So we said 6 and 2 is where it's coming in, and then this is the total enthalpy flux out. So this is the in. So where it's going out, we'll highlight that in our kind of our bluish color, just like the last one. So it's going out at 3 and it's going out at 1. So we just have to keep track of that. So the control volume, just to remind, let me erase the red control volume. It's really just the blue control volume that I'm interested in for this part of the problem, right? So I'm just erasing that part. So we have to take into account the blue ones. So 3 and 1 there. So these are the outs. And then this is our heat transfer term there. So we can solve for the Q dot in. Okay, I just need to make sure I've got all those numbers correct. I'm just give me a moment here while I just double check our numbers. Yeah, okay, all that looks good. So when you plug in the numbers for this, it comes out to be 6820 kilowatts. So we have that. We can plug it back in up into our expression for efficiency, and when you work out those numbers, it comes out to be about 31.5%. This is a particularly low efficiency especially for a cycle with reheat, but they're just somewhat arbitrary numbers. It's not based on reality. They're just example problem numbers. All right, again, nothing too special here on this particular example. The only thing you have to be careful of is keeping track of all the ins and outs of the boiler, because this again is where the heat is coming in. Okay. The very last part of the problem is sketch the cycle on a TS plot indicating states, paths, and isobars. So this is going to be a Rankine cycle with reheat. So here are our TS axes. We're going to draw, in this case, we're going to draw the vapor dome because it's a Rankine cycle and we deal with changes in phase. And we'll draw a typical Rankine cycle sketch here. So if I just sketch this in, I'm going to draw an isobar here first. Well, first of all, let me go back up to the picture and just remind us of where, I'm going to erase some of this. Going to remind us where each of the states are. So state 1 is coming out of the boiler, so that'll be at the highest, the highest pressure, highest temperature. So that's corresponding to this state. This is in a this will be in a superheated vapor region. If you look at that pressure and that specific enthalpy back in the property tables for water, you'll see it's in a superheated vapor region when you look at that. Of course, state 2 here is a saturated vapor because the quality is 1. State 3, what you'll find is that is also a superheated vapor when you go back to the thermodynamic property tables. State 4 is a saturated vapor because the quality is 1. State 5 is a saturated liquid because its quality is 0. In state 6, what you'll find if you look for these properties in the thermodynamic property tables, that'll be a compressed liquid. Okay, so just to put these points in perspective here, so here would be point 1 coming out of the boiler and into the first stage turbine. Then that goes, so this will be P1. And then from state 1 to state 2, state 2 is a saturated vapor, so that is now on just on the edge of the vapor dome. So let me sketch in that pressure. So P2 is less than P1. And then from state 2 to state 3, we go through the boiler again. So go back to the picture. So from state 2, we go into the boiler to do the reheat, and then back to state 3. So that's a constant pressure process from 2 to 3 because we're passing through the boiler. So that means we'll stay on this isobar up to state 3, which is a superheated vapor. Okay, so we're now at state 3, superheated vapor. So P2 and P3 are the same. And then from 3 to 4 is going through the second stage turbine. So 3 to 4, second stage turbine. And remember, state 4 is a saturated vapor at an even lower pressure. So I'll sketch that in. So here's isentropic, state 4. I should have given myself a little more space. So let me draw in that isobar. So here's state 4. So P4 is less than P2, which is less than P1. Okay, so now we're at state 4. That is leading into the condenser. Through the condenser, it goes all the way to being a saturated liquid. So this will be our state 5 here. So it's an isobaric process, so the same pressure. So P5 is equal to P4. We're at a saturated liquid state. Just remember, back up in our table, state 5 is a saturated liquid. It has 0 quality. State 6 is a compressed liquid, and we go to a higher pressure. We go back to the pressure at state 1, right? Same pressures. Because as you go through the boiler, that's a constant pressure process. Right? So we're a compressed liquid, and we go all the way back up to our state 6, which is on the same isobar as state 1. So here's a constant entropy, so we typically, it's not 100% thermodynamic, 100% isentropic efficiency through the pump, so looks like that. And then from 6 to 1 is an isobaric process through the boiler. So let me just highlight the path that we're taking. So we go first stage turbine, 1 to 2, then we go through the reheat through the boiler from 2 to 3. That's the same pressure from 2 to 3. 3 to 4 is the second stage turbine. 4 to 5 is through the condenser, which is a constant pressure process. 5 to 6 is through the pump, where we increase the pressure. And then 6 to 1 is going through the boiler, which is a constant pressure process. So that is what our TS diagram would look like for this particular example. All right. Looking back on the problem, hopefully none of this looks too new to you. I mean, we've done these first law analyses many times. We've drawn TS diagrams many times. We found thermal efficiency for power cycles many times. The only thing that's really different from what you've done previously is you just have a little more bookkeeping to keep track of because you go through 2 turbines and you go through the boiler twice. So it's just a little more bookkeeping, it gets a little busier, but hopefully all of it makes sense to you. And again, we talked about this in the lecture, but the reason we have these kind of reheat cycles is because what happens is you increase the average temperature where you're adding the heat. Just a reminder where we're adding heat, let me highlight that in a different color. So from 6 to 1 is passing through the boiler, and we add heat there, and then from 2 to 3 we're adding heat. So what we're trying to do there is we're trying to keep the average temperature where we add heat to a high value, which will help us increase our thermodynamic efficiency. Just remember that for a reversible power cycle, this is what our thermodynamic efficiency would be, our maximum thermodynamic efficiency, and if we can keep that TH really large, then we can get a higher efficiency, right? So as TH increase, oops, I just wrote TC, I meant to write TH. As TH increases, then TC over TH decreases. I should say put a down arrow there, which means that the efficiency should increase, right? So, of course, this is for a reversible thermodynamic cycle. Our real cycle isn't reversible because we have some, some inefficiency through our pumps and turbines, and there may be some inefficiency where we're adding the heat and such. But generally speaking, our actual efficiency for the cycle will tend to follow the theoretical, just kind of generally speaking. I mean, our maximum, it'll tend to follow that. So generally speaking, as we increase the hot reservoir, where we're adding the heat, we'll tend to have a higher efficiency. So that's why we do this reheat cycle. All right, we'll go ahead and end the example there.